Great. Great. Good morning, everyone. That snowstorm was pretty disappointing, wasn't it? At about midnight, there was maybe almost an inch. Although, not so much this morning. So today I want to spend maybe 2/3 of the time, half the time we'll see, probably 2/3, doing more with a dot product. So I'll say a little bit more about it, and we'll do some more exercises. And then I'd like to begin 14.1, which is partial derivatives, the actual calculus part. And we'll continue, I didn't write this down, but we'll continue with 14.1 and 14.2. We'll just sort of be stepping through the chapters the next week or so. I will be available for homework help today, 5 to 6, Ian 6:30 to 7:30. BL is botany lab. Occurred to me, like, we usually call it L3 here, L4. But maybe BL, I don't know. Anyway, I mean, it's Ian. It's where you would find Ian. I should have just put down Ian. Anyway, tomorrow, homework help for me, 3:30 to 4:30, Ian 6:30 to 7:30. There's that reading of I think, although there hasn't been a confirmation email about it, the Ta-Nehisi Coates reading from 4 to whenever. Could go several hours. Friday, homework help 2:30 to 3. That's going to be down in the ES classroom. I will have just taught the chaos class, and I thought rather than come up, I'll just stay down there. I've got the room reserved. And I'll need to leave 3 or a little bit after, because I have to head up to Bangor.
Where is it?
It's also known as the Gower classroom. It's the large classroom on the right in turrets. Yep. Questions? Other announcements? So let me review some of what I was saying towards the end last time about dot products, and then we'll just jump into some exercises. So dot products have a geometric life and an algebraic life. Up here, I've written this sort of geometric view. So it's a way of multiplying two vectors together. And you might think, well, we should just multiply the magnitudes together. But direction does matter. That's sort of the whole point of a vector. So it's a way of multiplying two vectors together, taking into account the extent to which they're in the same direction or not. So these are the magnitudes, and then this is the sort of directionality piece. Just a reminder. So if the angle between them is 0, they're pointing in the same direction. The magnitudes just multiply. If the angle between them is 90 degrees, they're pointing in perpendicular directions, orthogonal directions, and so the dot product would be 0. If this was flipped over this way, it would be negative. The vectors are sort of working against each other. So I said last time, and this is maybe a little bit subtle, but it's a really useful way to think about what dot products do. We take the magnitude of v1, so just sort of how to interpret this expression, and then magnitude of v1 times this expression. And what's this? Well, this is the side of this triangle. There's theta. It should be a v2, sorry. Hypotenuse. That's the adjacent. And so what that tells me is that the dot product is the magnitude of v1 times the part of v2 that's in the v1 direction, just this component. I could also tell the story the other way around. It's also the magnitude of v2 times the part of v1 that's in the v2 direction. So you could swap out v1 or v2. And then there's also v2x, v1y, v2y. There's also the component or algebraic form of this. So you just take the x components, multiply them together, the y components, the z components. If there are more components, you multiply those together, add them all up, and boom, you get the dot product. I think that ends my introductory remarks on dot products, unless there are any questions. So let's start. This is the same as the sheet I gave you yesterday, but I added some stuff on the back. So let's actually start with the pictures on the back, and then we'll move and work through the ones on the front. And we'll get up to, but not including, problem 11. Don't redo the ones you did already. And then we'll discuss. So let me say a little bit about the picture problems, largely so I can then erase this board and you can do other things on it. So we're looking to say, OK, so first of all, remember when you're doing a dot product, you want to put their the tails, the starting points of the vectors together. But vectors aren't fixed in space. You can always move them. And here, I would say this is greater than 0. You can see that because these vectors are they're not working together a lot, but they are working together a little bit. The angle here is less than 90 degrees. That's going to give you a positive number for the cosine. So again, I would say these vectors, they're not in the same direction entirely, but they're a little bit in the same direction. A little bit of B is going in the E direction. A little bit of B is going in the E direction, or equivalently, a little bit of E is going in the B direction. The dot product is symmetric. E dot B equals B dot E. You can see that from here. The dot product at the end of the day is just multiplication, and multiplication commutes. OK, so that's this one. D dot D is magnitude of D times magnitude of D. And that's always going to be greater than, well, unless D is 0, that'll always be greater than 0. And this also can be a useful way to write the magnitude of a vector. So just in general, V dot V equals magnitude squared. Let's see, last one, A and C, they are a little bit in the opposite direction. The angle here is greater than 90 degrees, not by much, but a little bit. And so that's going to give a negative answer for the dot product. If you've seen dot products before, one of the most common applications is the notion of work in physics. So work is force times distance, but only the force that's parallel to the displacement, which is written as a dot product. Work is F dot dr. So anyway, those of you who have physics pasts or physics presents, this is likely where you've seen dot products before. It comes up elsewhere in physics, but this is the most common and usually earliest place. OK, so as I said, let's now do the front of this, chug through, skipping 6 and 7 and stopping at 11. Sorry, was there a question? Or just a almost inaudible grunt? OK. All right.
I have a question.
OK, go for it.
When you look at the cosine curve,
Yeah.
I'm thinking it's not 180.
Yeah, I'm thinking you're right, too.
Okay.
And 8270. There we go, yeah. Next time I'll use radians, which I'm more comfortable with. OK, thanks. All right, so on the left board is the first 5 problems. I didn't number them. So I guess part of the magic, part of the power of a dot product is it lets you convert geometric statements into algebraic statements. And once you have algebra, you can turn the algebra crank that we've learned how to, to use, and you can figure things out. So something is perpendicular to something else. We now know like a way to write that as a formula. And that would be, we want the dot product to be 0. So if the dot product of 2 vectors is 0, those 2 vectors are perpendicular. So here, and I guess I sort of did this sort of pictorially in my head first. I said, OK, I claim this is going to be perpendicular to that. And why is that true? Well, if I take the dot product of these 2 vectors, I end up with 0. So they must be perpendicular. And I guess I really should draw a picture. So that might be A. And then that would be V. And then if I just found a perpendicular vector. If I multiply it by a scalar, say that would just like stretch. If I take V and I double it, it's still perpendicular to A. So that's what I did here. You could multiply it by pi or 3 or a half, whatever you feel like, or -1, flip it around. All right, so here's another vector. We can get a vector parallel to that by just multiplying it by a scalar. So here you are, you're running at some speed. Here I'm just like telling you run faster, but your direction hasn't changed. Here you're running slower, your direction hasn't changed. They're all parallel. Here, if we're looking for a unit vector in the direction of B, I need to find the magnitude of B. And then if I take vector B and divide it by its own magnitude, it now has magnitude 1, so it's a unit vector. So this vector W hat has length 1. How do people feel about this? That's OK? All right. OK, so let's move to something. Yeah?
So can we, I see how in that first one with the A and the vector B,
Yeah.
Did you just like swap? What did you do there? Did you just turn the coordinates around, or did you actually have to do like some kind of math around that? Or were you just able to be like, I know this and do like that?
Let's see. I swapped them around. So let's say you sort of didn't see that coming, and so let's say A was what, 3 minus 2, and then I'm looking for a V, and I don't know what. And then I would say I want A dot V to equal 0, and I need to solve for Vx and Vy. So so basically, I mean, this was sort of like making the answer just appear. So like if you couldn't just sort of like conjure it out of thin air, which like in the math writing thing, usually that says like by inspection we see that, which is just like I stared at until I figured it out. But that's like the slightly sometimes more obnoxious way of saying that. By inspection, notice that, which is slightly less obnoxious than saying one can see obviously that, which is like a surefire way to put down your reader who doesn't see that immediately. Anyway, so the point is, all right, so it's a good question. So like how would you, like if you didn't see that right away, what sort of crank would you turn to figure that out? So you say, all right, well, I know how to write down a general vector. I know the vector I'm given. And I want the dot product to be 0. So if I do that out, I'm going to get 3Vx minus 2Vy has to equal 0. And then you'll say, oh, that's a bummer. I can't, one equation, 2 unknowns. But then you'll suddenly realize that that gives you great freedom. You only need to find one pair that makes this equation true. And the reason that you can't solve it uniquely is that there's not a unique solution. And that's sort of what we're seeing geometrically. If I say, find me a vector parallel perpendicular to that, there's an infinite number of answers. Right? This vector, this vector, this vector, this vector, this vector, this vector, this vector. And that's what this says. There's an infinite number of answers to this equation. So this tells me that Vx is going to be 2/3 Vy. So you could set x equal to 1 and or Vy equal to 1 and solve for Vx or anything you feel like at this point. And it turns out, I mean, once you do, if you've done a few of these problems, you kind of come across that algorithm that you sort of flip the coordinates, change one sign, and you're done. Yeah. Great. And this will actually be a good warm-up for the thing I want to do next. Good. So that leads in nicely. So let me just say a little bit about this. So here's vector C. C is I plus 3j. Vector C dotted into I. Follow the rules. It's I components times a j component. There is no j component over here, so it just gives me this. C dot j hat gives me 3. And so in words, what does C dot j hat give you? In general, a vector C, yeah.
In the j direction.
Yep, well, it's is the j component. Or the j part. So again, dot product, its power is it lets you sort of do algebra with geometric things. So if like somebody hands you a vector and you don't care about the entire vector, you just want to know about the j part. How would you get that, like extract that algebraically from the vector? Well, you would just dot it into j. If you're doing something else, you don't care about the j part, you care about the I part, we'll just dot it into I, and you just have the I part. So dot products are a really powerful tool, sort of language for going back and forth between algebra and geometry. So what I want to do now is two things to hopefully impress upon you the power of vectors, and dot products in particular. So first, a quick little just sort of fun derivation, and then another derivation. Anyway, so I'm going to do two things, so each of which will probably be like 5 minutes. So all right, so we know about vectors, we know about dot products at this point. So suppose we have a situation like this, and I'm going to draw a picture. And then that vector is going to be C. And subtracting vectors, I have a hard time sort of seeing that right away. I always need to take the vector b and make it into the opposite vector b. So if I did a, and then here's minus b, so a plus minus b is going to give me c. People okay with this picture? Okay. So the subtracting vectors, again, it's something I never can see right away. I always have to stop and do this. Some people are better at subtracting vectors just in their mind. I don't know. Me. All right. So I'm going to do the following just because I can. I'm going to take C and dot it into itself. I mean, why not? And, well, C is A minus B. So that's the same as A minus B dotted into A minus B. All right. So let's do the left-hand side first. C dot C, what does that give me?
C magnitude squared.
C magnitude squared, yep. C squared. OK, so now dot products, we haven't proved this. The book doesn't, well, argues this a little bit. But I mean, it's basically multiplication. So it commutes, it distributes. Dot products generally behave the way you would expect multiplication to behave. So we can FOIL this thing out, only it's dot products we're foiling, but that's no big deal. A dot A minus B dot A minus A dot B plus b dot b. OK, so now a dot a is magnitude a squared. B dot b is magnitude b squared. Let's see, so I'll write this here. A squared plus b squared. And a dot b is b dot a. Order doesn't matter for dot products. This is going to be minus 2 a dot b. And then the last thing I'm going to do is say, oh, I know the geometric formula for the dot product. So I'm going to do this. C equals c squared equals a squared plus b squared minus 2a b cosine theta. Does that look familiar to anybody? Yeah, the high school students who are probably closest to the crucible of pre-calculus probably recognize this right away. Yeah, so this is a law of cosines. Something that some of you probably in pre-calc had to fight with at some point in your life. Anyway, it's a 3-line derivation once you know about dot products. Yeah.
Sorry, this is going a bit back, but I'm kind of confused by a minus b equals c.
So that's a sort of like non-obvious subtraction piece. So I'm going to start with a, and I'm going to add to a negative b. And then these two vectors, it's going to give c.
But when you do that, don't you usually, when you put like the base of b off the base of a?
But I'm putting the base of minus b. So I took b. So I'm turning subtraction into addition.
Right.
So I'm taking b and I'm turning b into minus b by flipping it around, and then I do adding vectors tip to tail. So I take this is a journey of a and then a journey of negative added to a journey of negative b, and I claim that that gives me this.
So you want to just like take b and flip it the other way? You want to make it b squared? And then get another bit?
I'm flipping it,
Right.
but then I need to set them not tail to tail,
Okay.
but tip to tail. Yeah.
Okay.
Yep.
Thank you.
Yep. Yeah, that's the sort of subtraction thing that I always have to talk myself through in the same way I just did. So anyway, the dot products have the law of cosines embedded in them. As some of you know, one of the things I like about math is like there's so little to remember. Like you just remember a couple things and then everything else follows from it. So here's a thing maybe from your past that you no longer have to even worry about remembering if you remember dot products. And more, I mean, it's not that big a deal because like you can Google law of cosines, it comes right up. But it sort of shows some of the power of this tool, vectors together with dot products. All right, so let's now talk about planes. So this is what some of you were looking at with problem 11. And maybe I'll start over here. All right, so planes, they're linear functions of two variables. And we've seen so far how to think about a plane in terms of slopes and an intercept. But there are other geometric ways we might want to think about a plane, like a plane that's tangent to a surface at a particular point. Again, sort of foreshadowing what's going to happen in the next chapter, just like we might talk about tangent lines in 1D calculus. So let's think about this. So here's the puzzle. I'm going to give you, like I did there. So imagine that we have a vector. We'll call it n for a normal vector. And I want to construct the equation of a plane that's perpendicular to that vector. So let me write this out. So n is going to be a plus b plus c, a, I, j. Okay, so now we're in 3 dimensions. And I want the equation of a plane that's perpendicular to n and goes through x naught, y naught, z naught. So the picture here is that somebody says, just chooses a direction, and then we want a plane perpendicular to that. And so there are lots of planes that could be perpendicular to that. And so then to uniquely specify the plane, if I pick one point on the plane, then I know which of those infinite number of planes to choose. All right, so now I'm going to attempt to draw all right, so here's the picture. N is the vector pointing in some direction. I should mention that this is pretty much an exact, this derivation is in the book. So you could also just follow along the book, or if you don't like my pictures or don't like your pictures, there are pictures in the book. This thing was not from the book. OK, so we've got this vector pointing in some direction, and this plane is perpendicular to that. And the value of the plane at some particular point, we know one point on the plane, x naught, y naught, z naught. We want to know what's the equation for this plane. So this looks like this might be a hard problem, but with dot products, it's easy. That's the narrative I'm going to try to make this. So don't despair. And the key is that dot products let us take a statement, something is perpendicular to something else, and turn it into algebra. And then algebra gives us the equation. It's going to happen in like 2 or 3 steps. So this is going to be a point x, y, z that's on the plane. And of course, there are lots of other points. There's an x, y, z. There's an x, y, z. There's an x, y, z. We want to know all the x, y, z pairs or triples that are on this plane. So I'm going to write a vector like this. And this vector points from this point, which it's not the origin. We can kind of think of it as origin, to some other point on the plane. So how would I write down an expression for v, this vector? It's a displacement vector, yeah.
The dot product of that and that equals 0?
Yes, although you're one step ahead of me. First, I want to come up with an expression for v, and then I'm going to dot it into n to set it equals 0. So how do we think about, so v is a displacement. How do we think about displacement vectors? Yeah, x minus. So it's how far you go in the x direction, in the j direction. And now we know how to write down the equation of a plane. So we're almost done. We should probably, like, I guess, write that out. So if I'm going to dot, right, so when we dot things together, we multiply the x's, we multiply the y's, we multiply the z's. So if I multiply the x's, that's this. Almost too far apart for me to reach. If I multiply the y's, that's that. The z's, it's that. I'm trying to save a little bit of chalk and not write this all out. So what I'm saying is this is going to be x minus x naught times a, y minus y naught, b, z minus z naught. So I sort of skipped a step there. So let me write one more form of this. And again, these equations are in the textbook, so if you don't feel like writing, no need. So what I did was I just pushed like all this x naught, y naught, z naught junk. I just pushed that over to the right-hand side. And it said, I don't want to write it all. Let's call it d. And then d is just that. So this is a kind of nice, I think, tight, fairly tight expression. So the point of going through this is twofold. One is this is actually a somewhat useful formula. I think we'll end up using it in chapter 14. And again, it also sort of illustrates some of the power of vectors, and particularly the dot product, connecting algebra to geometry. So let's take a moment, just a quick sort of plug-in problem. It'll be a break from me talking. Give number 11 a try, and we'll see if there are any issues with that, and then we'll start chapter 14. So first, just again, another picture of what's going on. So you're given this vector v, 3 minus 2, 1. And that's, in this sort of lame drawing, a vector in this direction. So this is the x direction, 3 in the x direction, minus 2 in the y direction, and up 1. So then we're looking for a plane that's perpendicular to this vector. And the answer is, well, there's an infinite number of them. You can imagine like a plane, it's here, 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 here. So you'll have, like, all of space could be filled with these planes, all of which are perpendicular to this. So like, I'm sort of picturing like pages in an infinite book, or like some sort of flaky millefeuille type of pastry that the entire universe has been partitioned into, and they're just all these like flakes or planes. And so in order to choose one particular page or one particular flake from that pastry, we need to specify one point, and that will get us a unique plane. So then we use the machinery that we developed over there, and the machinery leads to a pretty nice formula: ax plus by plus cz equals d. So the a, b, c, those are the components of the normal vector. And then d, what's d? Well, d involves the point that it goes through, point in space, that this particular point. And so if I plug into this formula, I get 2. So that's an equation of that plane. So again, this sort of gives a little practice of sort of the power of dot products, and also at the end of the day, you get a kind of useful formula that we'll use a little bit in chapter 14, I think. Are there questions on this one? All right. So we will now leave vectors behind for a couple days. And but don't forget them, because you'll need them soon. And we're going to turn to derivatives. So the calculus is actually beginning. And after today, it's just not going to stop. So probably some erasing this. Okay. All right. All right, so what do we remember about the derivative in one dimension? Different ways. It's the slope. Derivative, right, so, all right. What else do we remember? What are various, let's see, ways of sort of thinking about what it is? Words, pictures, numbers. This is like free associate. See what memories come up.
Product.
It's product rule. We'll get to that soon. So what sorry, I'm not at chain rule. I'm sorry, you guys are getting way ahead of me. Sorry. So what I'm not asking the question well. So I'm thinking of like difference quotients. Remember those? Like so how to write this? So it's rise over run. How much f changes if we change x by a bit? And then we're interested ultimately in the limit that delta x goes to 0. So if you're given a table of numbers, you can estimate, or a graph, you can estimate, well, you can estimate the slope, or you can stop the graph, or you can estimate the change from the numbers you're given. And so the notation here is f prime, or sometimes df dx. All right. So now let's think about 2D. So the idea is, we've seen that when we have a function of two variables, one way to think about it is to turn it into a function of one variable. So like you were given f of x and y, and I would say, like, well, what does f of x4 look like? And say, oh, well, that's just a one-dimensional function, just back to a curve. So what we'll start doing is by just saying, OK, well, now we're going to have initially just two derivatives. So we're going to think about, right, so if we've got, let's see, so we've got f of x here. We've got f of x, y here. And so I could do something like, say, rate of change of f(x, y). I don't know why I wrote that down there. I guess I'll just keep going in this column. With respect. So I like ask, how does the function change if I change x? And all of a sudden, we're back to 1D calculus, because like y is no longer a variable. So that just says, all right, if I walk in the x direction, what's the slope? You already know how to do that, actually. So in some measure, the first part of multivariable calculus is like shockingly, almost disappointingly easy. You already know how to do, like, there's really no difference between 1 and 2D at one level. But the notation is an awful lot more impressive. So one would write this like this with a lowercase x. That would mean the derivative of f with respect to x. That's maybe not so impressive. More impressive is this. And that's not just bad handwriting. These are like curly Ds. And these indicate that this is a partial derivative. A partial derivative. It's not the whole story. Right? We want to know how f is changing, how z is changing. And this tells us just how it would change if you changed x. To get the whole deal, you'll have to know how it would change if you changed both x and y. All right, that may be all right, so now you know enough about partial derivatives to start calculating them. So give this sheet a try. And so we'll spend 5 or 10 minutes on this, and then 5 or 10 minutes talking about it, and we'll call it a day. All right, so we have about 10 minutes left. So let me sort of say a few things about this problem. So h of x, what is that? That's how h temperature, I really would have used capital T, but anyway. That's how the temperature is changing in the x direction at the particular spot x at the particular time t. This is how h is changing in the t direction at the particular time x, the particular time t, although usually we don't think of t as a direction. So this is saying, like, if you're standing at a particular point x, at what rate are you warming or cooling? So for hx, I didn't hear any objection, so I'm guessing I did this right. But does anybody get a similar thing? OK, that's somewhat comforting. I was squinting at this, thinking, do I need to take my reading glasses out? So you go to the point 8,5, and you say, all right, if I go in the x direction, I'm start at this point, and I go in the x direction, what's going on? And reading the contour lines, right, so this, I said, all right, let's say this is right on the t equals 25 contour line. If I go 7 to the right, it appears like I go down 5. And what are the units on the 5, by the way? You go down 5 what? Yeah, that's degrees, and this is, what is this, inches? Meters, OK, good. And then at the same point, if I go in the up, that's the sort of time direction in this. If I go up 5, if I take a step of 35-ish, I'm up 5 degrees. So this is going to be degrees per hour per minute. Yeah, if this was hours, that'd be a pretty lame heater. It'd be like a candle or something. So again, units can be helpful for interpreting these sorts of things, right? So degrees per minute, oh, that's like how much we're getting, how much warmer we're getting. And then this is a less sort of, so we're kind of used to thinking about this, particularly in Maine winters. This is often negative. This is a less obvious sort of thing, but you're maybe used to this. There's warmer and colder parts of rooms. Some of you like the warmer parts, some of you like the colder parts. All right, so let's see. So h of x, is that going to be positive or negative or both or neither? What do we think about h of x? Negative, yeah. And what are some ways to make that argument? Yep. So that's sort of that's the kind of the physics argument. Farther away from the heater, you're going to get colder. Again, a hard-learned lesson. My cats have figured that out. They go very close to the wood stove in the winter. Pretty much all mammals in my house are close to the wood stove in the winter. Or you could also see this like more geometrically. If you look at this in the contour lines, and you just say, all right, if I move to the right, I'm going downhill. So that's the same, that's a sort of the geometric picture. And then t, if you go up, you're going uphill in this mountain contour map. And also, hopefully, unless you're in Ian's house with a broken heater, as the heater is on longer and longer, things should be getting warmer. Eventually, maybe the thermostat would kick in, and it would stop, but that's not in this picture. So, all right, so now we're doing two-dimensional calculus. And you might be thinking, this is very similar to one-dimensional calculus. And you're right, it is. So, and you can already sort of smell, like the chain rule is going to be the same chain rule. Algebra is going to be the same algebra, just like this was the same sort of thing. It's just you're reading things off a contour map instead of a one-dimensional map. So what we'll do Friday, we'll spend a little more on 14.1, some of these kind of interpretation word picture problems. And then we'll churn through 14.2, which will let you reacquaint yourself with the chain and product rule and fun things like that. So I can stick around for a few minutes. I've got a meeting to go to a little bit after 11. So if there are any immediate questions, I can stick around here. And then there's the homework help times up there.